Okay, so today we're going to talk about summation equations and the difference between equilibrium and non-equilibrium situations. Okay, so there's a couple things you got to know. You need to know what net forces are. Okay, so net forces, these are the total force and that can mean a resistance force, air resistance, friction, something resistance, along with whatever's applied or pulled. And it has a symbol, and it's a Greek letter, sigma. Which means sum. Okay? So when we have motion, like a constant velocity or not moving, you have something called you're at equilibrium. Okay. So at equilibrium, your net force is equal to 0 newtons. That's not on, that's 0 newtons, okay? So there's two different types of equilibrium. There's static equilibrium, okay, and this is when the object is stationary. Which means it's not moving. Okay, so in this case, the forces are balanced. Okay, and then you've got dynamic equilibrium. And this is when you have an object moving at constant velocity. Okay, so this means forces are balanced. And I'm just going to put on here just something for later. A equals 0 meters per second squared. So it's not accelerating. Constant velocity means it's not accelerating. Okay? Now, okay, so when something is moving and it's accelerating, you have something called dynamic motion, and that's non-equilibrium. Okay, so non-equilibrium, this means you have an unbalanced force because the object is accelerating. Okay, so in this case, your net force would not equal 0 newtons. Okay? Instead, your net force would be equal to something else that we'll talk about when we talk about unbalanced forces. Okay? Now, let's go over our directions real quick, just so that we know our directions. Okay, so vector direction, so you want to draw like a compass kind of situation, right? So if something is going up, it's in the positive direction. If something is going down, it's in the negative direction. If something is going left, it's in the negative direction. If something is going right, it's in the positive direction. Okay? So it's important that we remember our directions and our signs for our directions. All right, so I want to go back to our notes from the first day, and let's add summation equations for everything. Okay, so we're going to kind of flip back a little bit. To our free body diagrams. Okay? All right, so this first one, you have an object that is pushed at a constant velocity. Okay, so what does that mean? If you see the words constant velocity, okay, then that is in dynamic equilibrium. Okay? So if it's in dynamic equilibrium, then the sum of our net force in any direction is equal to 0. So we have to do net forces in the x and in the y. So your net force in the x direction, okay, is going to be everything in the x plane, the horizontal plane. So that's our friction plus our force applied, and because it's in dynamic equilibrium, that equals 0, or 0 newtons, sorry. Okay, it's also not moving up or down. So if it's not moving up or down, it's also in equilibrium in the y plane, so that's this part, the part that goes up and down. So then your net force in the y direction would be the normal force plus the weight, and that equals 0 newtons. Okay? All right, so let's look at the second one. Okay, we have a wagon pulled horizontally along a sidewalk with an angle from the horizontal at constant velocity. See constant velocity? Okay, that means we're at equilibrium. Okay, so my sum of my net forces in the x direction is equal to friction plus ftx. And that has to equal 0 newtons. In the y direction, it's not moving up or down, it's moving horizontally. So if it's not moving up or down, it's in equilibrium. So my net force in the y direction is equal to normal plus Fty plus my weight. It's everything in the y plane, and that's 0 newtons because it's in equilibrium. Okay. Next one. An object is at rest on an incline. At rest means that it's stationary. So if it's stationary, it's in static equilibrium. Okay? Static equilibrium. That means everything equals 0. All of our summation equations equal 0. Now, the plane is tilted on an incline. So the things that are parallel to the surface of our incline are our x stuff. So the sum of net forces in the x direction is equal to friction plus Fgx, and that equals 0 newtons. Now these things, see this one, right? This is the y plane. So the part that's perpendicular to the incline would be our y. Notice our weight, Fg, is not included in that. Okay, just Fgy and normal. That's all you should have. So your sum of your net forces in the y direction are your normal plus your Fgy, and that equals 0 newtons. Okay, so next page. Now you have an object is in free fall. Okay, so if it's in free fall, okay, it's accelerating. So this is accelerating. So this is what you call non-equilibrium. Okay. So that means my net force in at least one direction is not equal to 0. So in this case, I don't have any F net in the x, so I just say my F net in the x equals 0. It doesn't really need an equation, but it's 0. You do need to note that there's nothing going on in the x direction. But now my F net in the y direction is equal to FG, because that's the only thing there in the y direction. So it's FG. Okay. Okay, last one. Now you have an object falling at terminal velocity. So again, look at that. Ooh, that means it's at constant velocity. So if it's at constant velocity, this is dynamic equilibrium. Okay? So it's in dynamic equilibrium. Now it's important to note again, your net force in the x direction is 0 newtons because there's nothing there. Okay? You still have to write it. Your net force in the y direction would be just what you see in the y, the friction plus the gravitational, and since it's in dynamic equilibrium, that equals 0 newtons. Okay, so now I would like for you, and you can just do this in your notes. You're going to have a little activity you're going to do in the lab, okay? And so what I basically want you to do is, we'll call this FBD extra practice, okay? And so I want you to divide your paper in half, and then, it's going to be hard to see, and then divide that in half, and then divide each of those sections in half again. So you should have 1, 2, 3, 4, 5, 6, and 7, 8. Okay? And then you're going to go to the lab stations, and there's a little activity sitting out for you that I want you to write. It says for each of the following scenarios, you're going to draw a free body diagram and write the summation equations. And there's 8 situations, and you're just going to write them on your paper and then come and sit back down when you're done. Okay? And we'll go over the answers. Actually, I think the answers are on the back of the page, so if you get stuck, you can look at them. Okay? Okay, now that you're all done with the fun stuff in the lab, we're going to take a few more notes. Now we're going to stick some math in here. Now that you know how to write free body diagrams and you know how to write summation equations, we're just going to add a teensy bit of math. Okay, so let's say I had, I'm just going to jump right in. A stapler rests on the desk. Okay. So first I'm going to draw my free body diagram for that. Okay, so here's my stapler sitting on my desk. It has weight. Okay, let's say the stapler is, let's see, I don't know, 5 kilograms. Stapler. So I have FG. I'm going to write 5 kilograms in the middle just to remind me that thing has mass. Okay, and then I have normal force because it's sitting on the desk, okay? So I can go ahead and calculate my weight. My weight is Fg and it equals mg. So then Fg equals 5 times negative 9.81. It's negative because which way is it going? It's going down. Okay, so then let's stick that on my calculator. 5 times negative 9.81 equals negative 49.05 newtons.